All right, so in this video we're going to look at solving trigonometric equations where the trig function might be raised to a power higher than 2. So a power, well, 2 or higher, so greater than or equal to 2. Okay, so if you remember when you solved algebraic equations, that polynomial equations that were degree 2 or higher, your common techniques, depending on the structure of the problem, might be to use a square root, or a root in general, a cube root maybe, to undo an exponent, a square, for example, or factoring. So I'm assuming you have knowledge of both of these techniques that we'll be using here. And I just realized I left an N out on my spelling of techniques. Sorry about that. So let's jump right into it. Nothing terribly advanced here. We're just going to use what we know about solving some basic trig equations along with what we know about square roots and factoring. Okay, so let's say that I want to solve this equation, 9 sine squared of alpha minus 1 equals 0. So the first thing I'm going to do is isolate the sine of alpha, and then we'll figure out what alpha could be. So I'll add 1 and divide by 9. So sine squared of alpha equals 1/9. And then I'll take the square root of both sides and see that sine of alpha could be plus or minus 1/3. So in other words, the sine of the unknown angle alpha could be 1/3, or the sine of that unknown angle alpha could be negative 1/3. So now I'm going to draw pictures of what alpha could be, understanding that my opposite over hypotenuse could be 1/3 or could be negative 1/3. So if I'm looking at sine equaling positive 1/3, I could have a opposite side of 1 with a hypotenuse of 3. So I get these two possibilities. Or if sine is negative, I could have an opposite side of negative 1 with a hypotenuse of 3 and get these two possibilities. Okay? Now my reference angle in all 4 of these triangles, because they're the same reference triangle, so alpha bar, the reference angle, is going to be the sine inverse of positive 1/3, because the reference angle is independent of the pluses or minuses. Okay? So now what I'm going to do is try to use alpha, right? That's the angle measured at each of these distances from the x-axis. So the first thing I'm going to do is I realize that these angles here are separated by pi in both directions. So I can describe all of those angles in one statement. So for example, alpha equals, well, the first angle that lands here is alpha bar, right? This is alpha bar, which is sine inverse of 1/3. That is not one of our nice angles, so I'm just going to call it sine inverse of 1/3. And that angle lands right here in the first quadrant. Then to get the next angle that lands opposite it, I need to add pi. And to get the next one after that, I'm going to add pi again to come back. So I'm going to add multiples of pi to describe all of these answers. So k times pi. So that describes everything in green. Now let's do red and describe these guys. So the first angle is this guy. So alpha could be that, which is just short of pi. In fact, it's pi, because here's pi. And then I need to subtract my reference angle. So pi minus sine inverse of 1/3. And because these guys, these two red angles, are separated by pi, I'll do plus k pi for that. And then I'll just state that, well, k has to be an integer. And that describes all of the possible angles that alpha could be. There are 4 of them within one rotation of the coordinate plane, but there's an infinite number of them if you continue to rotate in the positive or negative direction. Okay? So that's our first example. And we did that using a square root. Okay? So let's do another example. Example 2 I want to solve. And in this case, let's solve cosecant squared theta plus cosecant theta equals 0. Now, because one of these terms is squared and one of them is to the first power, I can't use a square root. I can't use a square root. So instead, I'm lucky enough to have a 0 on the right side. So what I'm going to do is I'm going to factor the left side. And I can see that those two terms have a cosecant of theta in common. So I'm going to factor out cosecant of theta. And when I do that for cosecant squared, it's going to leave behind a cosecant theta, because cosecant theta times cosecant theta is cosecant squared theta. And when I factor a cosecant theta out of cosecant theta, it leaves a plus 1, because cosecant theta times 1 is cosecant theta. And of course, that all equals 0. We know from basic algebra, if I multiply two things, here, cosecant theta and cosecant theta plus 1, when I multiply those together, I get 0. And the only way that can happen is if one of the two things you multiplied is 0 independently. So in that case, we know that the cosecant of theta has to be 0, or that cosecant of theta plus 1 has to be 0. Now let's go ahead and change these to maybe sine, because cosecant is the reciprocal of sine. So cosecant of theta, well, is 1 over sine of theta. So in other words, sine of theta would have to be the reciprocal of 0. So all I'm doing is the reciprocal of both sides. So the reciprocal of cosecant of theta is sine of theta. The reciprocal of 0 is 1 over 0, right? Because you could think of 0 as a fraction, 0 over 1. So when you flip it, it turns into 1 over 0. And what we see now is no matter what angle theta is, because I'm trying to solve for theta here, the angle, I can't use any angle and divide by 0. So this guy is impossible. So I know that there's no theta that's going to satisfy that portion, because you can't divide by 0. But coming over here to the second half, we can see that cosecant of theta equals -1, and now I can do the reciprocal of both sides again, so I can change it to the sine function that I'm used to. So sine of theta equals -1, if you think of it as a fraction, as -1 over +1. And if you flip that, +1 divided by -1, you still get -1. Now that's possible. In fact, if you draw a picture of that, sine of theta is -1 down here at 3 pi over 2. 3 pi over 2. That's the only place. So how do I describe every angle that lands here? Well, theta could be 3 pi over 2, and then I can just keep adding rotations of the circle to get the subsequent solutions. So plus 2k pi, where k is an integer. And those are all the solutions to the original equation. So in this case, we didn't use square roots, but we factored. Okay, let's do another. Example 3, we want to solve 2 cosine squared theta minus 1 equals cosine theta. Now again, we've got a squared cosine and a cosine to the first. So we can't use square roots. So instead we have to factor. But if I want to factor, I have to have 0 on one side. So don't forget that. So if I want 0 on one side, I can do that by subtracting my cosine of theta from both sides. And so the left side, if I put it in descending order, turns into 2 cosine squared theta minus cosine theta minus 1 equals 0 on the right side. And now this should look reminiscent of a polynomial. It looks like 2x squared minus x minus 1. If you think about x as being the cosine of theta, you've got 2x squared minus x minus 1. If you factor that, again, assuming you know how to factor, 2x times x gives you 2x squared. 1 times 1 gives you 1. And then you need a minus here to give you a negative 2x, and a plus here to give you a positive 1x, resulting in your negative 1x in the middle. So that's a quick summary of my process for factoring. So what this means, if I rewrite my blue equation using this, that means I can factor it the same way as I did this, but instead of x, use cosine of theta. So this turns into 2 cosine theta, and this turns into cosine theta, right? 2 cosine theta and cosine theta. And you can see if you multiply those together, you get 2 cosine squared theta. Then I've got my plus 1 and my minus 1. If you check, plus 1 times minus 1 gives us the negative 1. And last, you could check, you get negative 2 cosine theta plus 1 cosine theta. That gives us the negative cosine theta here that we had in the middle. So we've got it factored now, and just like the previous example, once it's factored and equals 0, I can conclude that one of my two factors has to be 0. One of the two things that multiplies together has to be 0. So I can say 2 cosine theta plus 1 has to be 0, or cosine of theta minus 1 has to be 0. And now let's work on the left equation first. I'll subtract my 1 and divide by 2 to get cosine theta by itself. Okay. On my second equation, I'll add 1 to see that cosine of theta equals 1. Now I'm going to draw a picture of all of these angles. So cosine is adjacent over hypotenuse. Adjacent over hypotenuse. So my horizontal side is negative 1, my hypotenuse is 2. So I'm going to go left 1 and hypotenuse of 2. Okay. Now the reference angle for both of these, the reference angle there, theta bar, is cosine inverse of positive 1/2, which that is one of our nice angles. That is pi over 3. Okay. So those two reference triangles tell us all the angles that make that statement true, that the cosine of theta is negative 1/2. And we'll describe those shortly. But let's go ahead and look at where cosine of theta equals 1. Cosine of theta equals 1 on the positive x-axis. So the adjacent side has to be 1. And the angle there is 0. Okay? So we've got 0. Then this angle here is, since our reference angle is pi over 3, we're just short of pi in the second quadrant. So this will be pi minus pi over 3, which equals 2 pi over 3. So this angle is 2 pi over 3. And this angle down here is past pi, so this will be pi plus the reference angle. So that's 4 pi over 3 for this angle. Okay? So we've got 0, 2 pi over 3, and 4 pi over 3. You might notice that those are separated by 2 pi over 3 intervals consistently. And so what we can do then is we can describe all of those theta solutions. Theta could be any of those. So my first angle that theta could be is 0. And then I'm going to add multiples of my 2 pi over 3 to knock out every other solution. So I'll do k times 2 pi over 3. Multiples of 2 pi over 3. So simplifying that, I don't need to write 0 plus. Adding 0 doesn't affect anything, so I'll just drop that off. And k times 2 pi over 3 is simply 2k pi over 3. And of course k has to be an integer. So this one's kind of a cool example where something sort of unexpected happens, and the solutions to these seemingly independent equations work very nicely together here and equally spaced, allowing us to write our answer very simply. You could also write this in 3 statements. You could describe all the angles that land here, and then you could say all the angles that land here, and then you could say all the angles that land there. That's perfectly acceptable as well. But I'm going to try to show you the little tips as we go along. Okay, so here's an example where we had to factor again, but we had to factor a trinomial, which is a little tougher than what we did in the previous example, where we had to factor out a greatest common factor, and that was it. Okay, let's do our last example. Solve. And this one is going to involve several things. So we're going to solve tangent to the fourth of x minus 13 times tangent squared of x plus 36 equals 0. Clearly, we can't use the square root or something to solve this because we've got different exponents involved. So we have to factor. And so I'm going to jump right into factoring this now. Luckily, the right side's already 0. To get tangent to the fourth, I'm going to put a tangent squared times a tangent squared. And then I need a 36. So the numbers I put here and here have to multiply to be 36, but they have to add to be a negative 13. Okay, so this goes back to your algebra days. You have to use minus 9 and minus 4. Okay. Now, this is still a higher degree equation. So you've got a couple options at this point. We could conclude that this guy equals 0 and this guy equals 0. That's fine and works perfectly well. You could also factor more because this is a difference of squares and this is a difference of squares. Okay? So either way, you'll get the same answer. Let's look at the difference of squares because we haven't explored that yet. So this guy is going to factor. If I break it down, it's going to be tangent of x times tangent of x to get my tan squared of x. And it's going to be plus 3 times minus 3 to get my negative 9. Similarly, this guy's going to do the same thing. Tan x plus 2 times tan x minus 2 equals 0. So now I've got four things multiplied together, four factors multiplied together to equal 0. So now, for that to happen, I don't know why my screen is jumping around, I apologize. So I know that tangent of x plus 3 equals 0, or tangent of x minus 3 equals 0, or tangent of x plus 2 equals 0, or tangent of x minus 2 equals 0. So in other words, tangent of x could be negative 3, tangent of x could be positive 3, tangent of x could be negative 2, or tangent of x could be positive 2. So we could put these guys on the same axis. Think of negative 3 over 1, 3 over 1. So if I'm looking at where tangent's negative, I know I'm dealing in quadrants 2 and 4. And this is opposite over adjacent for tangent. So my opposite side could be positive 3 with an adjacent side of negative 1, or vice versa, like this. And the reference angles for those, so x bar, is tan inverse of positive 3. Similarly, if tangent of x equals positive 3 over 1, I'm in quadrants 1 or 3. So negative 3 over negative 1 would give me a positive 3 ratio. Or I could have positive 3 over positive 1 to give me a positive 3 ratio. Luckily, the reference angle is the same. These are all the same reference triangle. So what we'll do is we'll describe these angles because they're separated by pi. So x equals this first angle. Well, in the first quadrant, the angle itself is going to be the same as the reference angle. So I've got tan inverse of 3, that's my first angle, but then I've got to rotate by pi as to hit all the subsequent angles on that yellow line. So plus k pi is going to knock out all the yellows. Or, to knock out all the greens, I have to know this angle, which is just short of pi, so it's going to be pi minus my reference angle. Okay? So x could be pi minus my reference angle, plus, because they're separated by pi, it's going to be plus k pi again. Similarly, when you do these guys, you'll get the same exact sort of picture, and you'll see that x could be tan inverse of 2 plus k pi, or x could be pi minus tan inverse of 2 plus k pi. And of course, for all of these, k could be an integer. So we have all these possible solutions for x in this case. So in this case, we had to factor something higher than degree 2, and we had to factor more than once. Or we could factor it once and then use the square root to finish it. Either way, you get the same answers.